Voy a hablar en inglés. Mi inglés es un poco broken English, but I hope you understand what I'm trying to say. In fact, I'm very glad to have to be invited in this Latin-Mag conference. It's a very good initiative of the new board of Latin-Mag. And in this way, it's even though we are all closed in our homes, trying to be safe, we can talk to each other and keep going with our science in this pandemic period. So I would like to first say good morning, good afternoon, good evening for all of you. And the idea is to talk a little bit about the South Atlantic Magnetic Anomaly, but mostly on the side of the paleomagnetic record it has left, mostly on speleothems and also on rocks. So I'm going to talk about those two aspects. So since since we started to measure the magnetic field on Earth, that started in 1800s, at the beginning of the 1800s, with Gauss and Weber, those that are represented here in the Göttingen Observatory. The magnetic field has been decreasing, and this is the diagram indicating the dipole component of the magnetic field. And we see that it's getting down at a speed of about 5% per century. And here we have the record of observatories from that are reported in the IGRF 12, the chaos model, and also the GUFM1 model. All of them are green and showing this strong decay. So while the magnetic field is decaying, there's something else happening at the surface of the Earth. And we see that in the geomagnetic record as well, is that there's an increase in this magnetic anomaly. This anomaly represents a weak field. It's weaker than it was supposed to be. And this one is called the South Atlantic Geomagnetic Anomaly. And it covers nowadays most of South America, part of the Atlantic, and there is this kind of lobe going to the coast of Africa. This is the model of 2015, and this feature is very interesting because it shows the huge part of the anomaly is in South America, but we have now this new lobe is forming and expanding over the southwestern coast of Africa. So this anomaly has got a lot of attention from the media. So we have lots of news coming out about the anomaly, and in fact, it's going to the NASA is tracking this anomaly. It's very important because this anomaly, since the field is very weak, it's also a place where space hazards happens much more often than elsewhere in the world. So monitoring the anomaly is very important to know and to keep the satellites and even human flights on the space safe. So NASA says that the anomaly is going to split in half. That's because it's separated in two lobes. Then some suggesting that this anomaly is very old. There's a new paper showing that it may be there in the South Atlantic, at least since the 11 million years in the past. And some have also proposed that the fact that the anomaly is growing may indicate that and the field is decreasing, may indicate that the magnetic field may flip, may revert in the next thousands or hundreds of thousands of years. So there's a debate on if the increase of the anomaly, the decay of the field, is really going to result into a very soon reversal of the magnetic field. So in this talk, I'm going to talk first a little bit about the South Atlantic Magnetic Anomaly evolution, about reverse flux patches, about the archimagnetic record, the speleothem record, only very shortly 2 slides about the volcanic record, and then discuss the origin of the anomaly and the perspectives about what we are going to do and what we are doing to understand better this feature. So here's the series of maps of the geomagnetic field of the Earth at the surface from the GUFM1 model. So this was published by Hartman and Parker in 2009. And in this paper, they do a very comprehensive description of the South Atlantic Anomaly and the evolution of the anomaly through time. So it starts using the model of the GUFM1 model. The anomaly, the center of the anomaly would be placed in the 1500s at the coast of Africa, around Namibia and Angola. And then with time, the anomaly started to migrate westward, and not only that, increasing in size and also increasing in intensity, meaning that the field became more and more weak in this region. And here is the situation they had at 2005. We saw that now in 2015, the anomaly is even bigger than that. And it's splitting, apparently splitting in two. So the anomaly is increasing since at least 500 years and migrating from Africa, from east to west. So this is the characteristic of the anomaly we have. And there are 2 main ways to track the anomaly. One is to define a threshold of intensity. Usually people use 32,000 nanotesla. And then you track the area of the anomaly and how this area increases or decreases. And we know it's increasing. The other way to track is to track the center of the anomaly, the position of where the field is the weakest. And then we can track the anomaly here, for example, between 1840 to 2015, showing the evolution of the anomaly through time. So according to those 2 ways of tracking, we know that the anomaly is going from east to west, and the area, the surface of the anomaly is increasing with time. So here is the team we put together to think about this anomaly, to work on the different materials like speleothems, people from the caves, people working on archaeological material, and also our colleagues working on modeling. All of them are going to take part in parts of the bits of this project. So I'm going to start with our colleagues working on reverse flux patches, why they are important. So we know that the anomaly is the magnetic field is decaying through time. But we also know, and that this has been shown by also in Amit in 2006, that this decrease is followed by an increase in the reverse flux of the field at the core mantle boundary in the southern hemisphere, and the decrease of the normal flux in the southern hemisphere. Note that the northern hemisphere keeps more or less continuous or constant, but there's a very strong change in increasing reverse flux and decreasing normal flux in the southern hemisphere. So it seems that the southern hemisphere bears lots of the answer to this major decrease of the magnetic dipole. And this is happening at the core mantle boundary. So what are those reverse flux patches or normal flux patches? So the reverse flux patches are those patches of flux that are in the opposite direction to what they are supposed to be, considering the different hemispheres. And in the southern hemisphere, we have those very large patches, and this is for So sorry, I'm having this over. And we have together with those reverse patches, we have also the normal patches that are here. So those are patches in which the field is more intense than it's supposed to be. And those reverse and normal patches, they have different origins. For the, sorry. For the normal patches, they are mostly related to the tangent cylinder position. So they are related to downwelling flux at the tangent cylinder. Whereas the reverse flux patches are related to upwelling and diffusion at the core mantle boundary, and usually related to, that may be related to variation in the heat flux at the core mantle boundary. So what Felipe Terranova has done in his master and PhD, first was to track those reverse flux patches, so developing an algorithm to define what automatically what a reverse flux patch was, then having this defining it, tracking it through time. And what he has observed is that there are longitudes that are in which those patches are more often observed. So we have reverse flux patches that are more typically concentrated in specific longitudes. And that's very interesting, because then we can compare this to the mantle structure at the core mantle boundary. And when we do that, we see that here we have models of velocity anomaly, meaning places that are hotter or cooler, that are indicated by this pink line. And those are the places where we have more or less those more thinner lines, occurrences of reverse flux patches. Then we see that they coincide, meaning that when we have those anomalies in the mantle, in terms of if they are cooler or warmer, we would have a larger amount of reverse flux patches, meaning that those expulsions of field are in fact related to a lateral contrast of heat flux. That's very interesting, because it suggests that there should be a mantle control on those features. And if that's true, since the mantle doesn't evolve as fast as the magnetic field itself, those features must be recurrent through time. So then, to investigate the field in the past, beyond the observatories, we went to study archimagnetic material. So here we have the map of South America. You don't have that many archimagnetic results for South America. And when we started to study the archimagnetism in South America, we were very puzzled to discover that there was a large unknown. People didn't really know what was the evolution of the simplest parameter of the magnetic field, that was the dipole. So here is the results constrained by the geomagnetic observations. And here, before that, is what we know from archimagnetic results. And we see that there are several different available models. This is an ancient figure, so there are other possibilities for and new models that were done after this figure was made. And if we go to the past beyond that, it's even worse. And to understand why it's so hard to do those modelings in the deep past, we need to understand that the data is very scattered. And so we need more data, but we also need more high quality data to better constrain the evolution of the field to the past. So in South America, what we've done is that we went to 3 different places in Brazil, in Northeast Brazil and South Brazil. And then we collected samples from historic buildings, like the lighthouse in Salvador in Bahia, and some historical houses in São Paulo and Salvador, and Rio de Janeiro. Then we went to the Jesuitic missions in the border between Brazil, Argentina, and Paraguay, and to some farms in South Brazil. All of them, in all of them, we have the help of archaeologists to provide good ages for those archaeological artifacts. And then we use the classical Neo theory and then the classical measuring techniques like the EASY protocol developed by Lisa Talks and collaborators that essentially says that we can apply the artificial thermal remanence to a rock or artifact. This artificial remanence is going to be proportional to the remanence that was acquired at that time, and the constant of proportionality between the new remanence acquired in the laboratory and the ancient remanence that was acquired in nature, as well as the ratio between the two intensities, the intensity of the field in the past and the intensity of the field in the present day. And we can do that because there is a relation between magnetization and the field, and this relation at first approximation is a linear relation. So it's a well known technique, but there are lots of problems with this technique because there are a lot of corrections we need to do, and the success rate is also very low because there are lots of experimental problems that can happen during the procedure. So doing it very carefully and eliminating all the samples that do not follow certain criteria provide a very good approximation of what was the intensity of the field in the past. So we have done those, we call those diagrams array diagrams, and they plot the remaining NRM during the double heating treatment and the thermal remanence acquired in the laboratory. So if this those points are straight, and if those checkpoints they match previous observations, it means that this direction is the quality is very high. And in those 4 examples I'm showing here, they are very high quality, and we have used all those points to build the evolution of the intensity of the field. So here's again the evolution from the data, and here in continuous lines are the models. And from the large set of results we had for South America, we then applied 3 criteria to choose the best ones to then reasoning about the magnetic field. So the first was the measurements that were accepted, measurements that could have those checks, and those checks were appropriate in terms of statistics of overlapping the old points. The data must comply to the statistical quality criteria defined by Patterson and collaborators in 2014. And also the data must present internal consistency at fragment level and also at site level. So if a result obeys to those criteria, it means that it would be accepted in our database. And after filtering, we have this. Note that now we have the results are very consistent from the youngest part of the model. That's very good. It means that they are consistent with the direct observations. And then we have some other results that are consistent with some models in the more ancient past. Then we can plot again now those results. Those are the results here, time and intensity for different regions of South America. Our results from Brazil, but also results from Argentina and Chile. And you see that those are the models for each region with the corresponding color. So note that we have those for Chile, Argentina, here South Brazil, Southeast Brazil, and for Northeast Brazil. But when we relocate all of them to the city of Pelotas in South Brazil, what we see is that those results, they are different, in fact. We have results from Chile on top of all of them, all of the others, and results from South Brazil a little bit to the south, to the below. So what we think is that maybe this is related to the influence of the South Atlantic Anomaly, because the anomaly is very important in this region, but it's not so, it was not, at least at a certain time, so intense at this western region of South America. To test that, what we have done is that we took those intensity values, and then we subtracted this from the dipole, from the model. And what we saw is that the reason is that if the result here is 0, it means that the field is very close to be dipolar. But if the result is very different from 0, and here we have but 1 sigma and 3 sigma, then eventually we would have very strong non-dipolar components present in the field. And it's interesting that until 1750, the field was more or less almost all of them fall in the dipolar field. And then we started to have a influence of non-dipolar components starting in 1750 or 1800, depending on where you put your limit. It means that the influence of those strong non-dipolar fields were there in South America, at least starting in 1800. So we have this, we suggest in this paper that the anomaly has arrived at this time in South America. But we could test this in other ways, and we could also compare those results with results obtained elsewhere. And to do that, we started to think of having results from continuous records and with very high resolution. And for that, we went to study the speleothems. So we have found a group of people working on caves. They had a very nice collection of speleothems that were very well dated. So we went there, and then we collected some speleothems and started to do some paleomagnetism on this. Speleothems, and particularly stalagmites, they grow almost continuously upward. And internally, they have layers that are usually very rich, very poor in magnetic materials, but they have magnetic materials, and those magnetic materials could be measured. They present several different, several advantages in relation to other sedimentary material. First, they are not compressed, so they don't have a change in inclination of the magnetization, because once they crystallize, they keep the shape and they are not deformed. They can be well dated by uranium thorium dating, and given if they have enough material, they can be those results can be reliable. And those studies in stalagmites, they started very early in 1979 is the first study. Some authors like Morinaga tried to understand how it works and how it worked, and they did a artificial stalagmite inside his cryogenic, and then he defined that with this artificial stalagmite, he could show that the blocking time was in about 15 minutes, meaning that the blocking time for stalagmites is very fast. And we know that, so this suggests that we can rely in those kinds of rocks to have a very, not only continuous, but also a very precise relation between the age of the rock and the lock-in of magnetization. Then we have other studies like LASCO working on excursions using stalagmites, showing that they can record those excursions very well, nicely, and then providing a very high, very precise dating for the excursion. This is unprecedentedly precise compared to other techniques based on the soft sediments. But stalagmites can also preserve the record for periods of time that are not at the scale of the excursion. If you have a very fast-growing stalagmite, you can preserve the record of the field at the scale you're interested in, that is in the scale of thousands of years. So I have an example here. I need to show this. This is a stalagmite in Morocco that's being studied by Janine Cabo in her PhD. So here, each specimen here means about 100 years. And here's the very well known curve for the magnetic field in Central Europe that can be translated to transferred to Morocco. And here is the result indicating by points obtained in those stalagmites that Janine is working on. So it means that in this region that has lots, hundreds, thousands of results that can be compared with in terms of archeomagnetism, the stalagmite result follows very nicely the curve, even showing those very fast variations in the field that are mapped using the archeomagnetic results. And the potential for study of stalagmites is enormous. We have tested several different stalagmites from Brazil, and all of them show NRMs that are higher than 10 to minus 8 or 10 to minus 7. So they are, we can measure them with the cryogenic. All stalagmites that we studied, they provided NRMs that are measurable using the cryogenic magnetometer. And interesting also is that they have a very similar mineralogy from stalagmite to stalagmite. All of them follow in the extracellular magnetite field in the Eglis diagram, suggesting that we are dealing with magnetite that came from the soil together with the drip water, and also indicating that we are dealing with very fine-grained magnetite at the stability field. So we have stable magnetization with fine-grained material in a sediment that's precipitating very fast. It doesn't deform, so it's an almost ideal material. So we can compare the results we then obtained in Brazil in some stalagmites with results obtained from Africa. Here we have a map of the South Atlantic Anomaly that's usually limited by this pale blue color. Here we have the sites that were studied by Tardone and Hari, 2018 in Africa. And we started to study something, a speleothem from central Brazil here to compare. The interesting thing about this result in Tardone is that he used it to suggest that the South Atlantic Anomaly was 1,200 years old. Why? Because the archaeomagnetic results he obtained in that region, and then later Hare as well, with the paleo direction, showed a very fast changes in intensity here, but also in direction. And those changes in intensity that were very fast, and also the changes in direction that were fast, they coincided in time. And so we have a first fast change in 1,200, and then another fast change in about 1,800. So in our case, the idea was to study if this kind of variation could be found in South America. So we used some stalagmites from central Brazil. Each sample that was cut from the stalagmite provided a interval of time of about 30 to 40 years. Those are the Zeiderveld diagrams for those directions. Here's the pseudo-Tellier RI diagram showing the fitting of the relative paleointensity. And here we have the directional data for those records. So we show here that we have the two speleothems in terms of inclination following the prediction of the CAUS-3 and RKO3 model. But then when we go to declination, it's clear that the speleothem results, they follow better the ARC3 model. When we go to the paleointensity, it's also clear that the speleothem record, even though it's very noisy, it follows nicely the intensity of the ARC3 model. Note here that we have also put in the figure the absolute intensity results obtained from archaeomagnetic material. So we see that the speleothem record is also consistent with the archaeomagnetic record. Then we also observed those very fast and sharp variations. And the fast movements, we considered fast movements when they were higher than 0.1 degree per year, just like Hari has done in 2018. And those fast movements from Africa to South America, they had a 200 years delay between the two periods. So we suggested that, in fact, those fast movements, the first and the second, in Africa and South America, were an expression of the South Atlantic Anomaly as passing 2 times from Africa to South America. So the South Atlantic Anomaly would be recurrent. And if that's the case, then the idea of a top-down control, meaning a mantle control on the birth of the anomaly and its evolution, is favored in the case of our results. We then try to test that, how those variations could be formed if, in which situation a reverse flux patch would induce those variations that we observed on the surface. So in 2017, Terranova has shown that it's not, we cannot relate a reverse flux patch directly to an anomaly in the surface, because the kernel, the relation is not straightforward. So to have a anomaly like the South Atlantic Anomaly in this way, we must have not only a reverse flux patch, but also a normal flux patch together. So we need to have several different patches to promote this migration of the anomaly from east to west. So in this, just to represent that, here we have a surface intensity map. Here's the geomagnetic field, and here's the radial field at the core mantle boundary. So what we see is that those patches here, they have a relation between, they provide a relation between this and the anomaly that is really not straightforward. We have a patches that are here, but then we have the anomaly that is very close, more closer to the tropical latitudes and close to the equator. So we cannot relate it just a flux patch and an anomaly. So what we proposed in the 2018 paper is that to provide a very fast variation in intensity, declination, inclination, and the fact that they are not necessarily coupled, all of three, we would need not only a westward drift of a patch, but also a intensification of the patch, the expansion of the patch, and the action of another patch in the south that would be a patch located in Patagonia, in southern South America. So it's a kind of jiggle between three patches that would provide what we observe in terms of evolution of the South Atlantic Anomaly. Then we decided to go a little bit further in the past. Then we went to another cave in Brazil, and this is a work in progress by Plínio Jaqueto, and it's part of his thesis. And here are the results we have for this new cave in black. Here are the results we have in red for the alio that I've shown before. Then here are the results we have for the new cave, and they followed very nicely the inclination, declination of part of the models. Then they not necessarily follow well the models for the periods after 4,500. And here's the results of intensity that also follow the models, because the models coincide here in this period, but then they go closer to this big mud model that was proposed some years ago. We can even try to go further back in the past, and then I'm going to draw your attention to some work that has been done in St. Helens in Tristan da Cunha Islands. So this is Tristan da Cunha work showing that there are very fast variations in the magnetic field. And those fast variations in the magnetic field that are observed in Tristan da Cunha are suggested to be related to something like a South Atlantic anomaly crossing over this island. More recently, in 2020, in the last month, there is a paper that came out by Engbers and others, in which they show this in a different manner, like showing that the paleomagnetic record of St. Helens, that's another island in between South America and Africa. And this, the paleomagnetic record of this island is shows very large dispersion, much higher than the G model, and much higher than the dispersion obtained from other places in the world that are not crossed by the South Atlantic Anomaly, that are not supposed to be crossed by the South Atlantic Anomaly. So they suggest that this high dispersion is related to something like the Atlantic Anomaly passing through this island at about 11 millions of years in the past. So if this Engbers result and this or the result for Tristan da Cunha, if they are right, it means that this anomaly is there and showing this recurrency through time for tens of millions of years in the past. So And if that's true, then the idea of a mantle control and the fact that we have this those mantle anomalies at the core mantle boundary sitting there for hundreds of millions of years may be a reason why this anomaly happens there, and may suggest that this is really a recurrent phenomenon at this scale of time. So in terms of perspectives, what we are trying to do, so then we are now trying to understand through the work of Terra Nova how that anomaly works in terms of the internal fluctuations of the field and the direct influence of the mantle by modeling this, so like using a toy model for the magnetic field and changing the heat flux at the core mantle boundary in a numerical modeling, and see how this responds in terms of the variation of the field. If we put a contrast in terms of heat flux at the core mantle boundary, does that would provide a more variable direction in that location, or a higher dispersion and so on. Something else we are starting to do is to study the Paleomagnetism of Trindade. Is an island in the coast of Brazil. And in there we have volcanic rocks that are dated between 3.9 and 0.25 million years. This is the PhD of Natalia Pasqualone, and she has already sampled the island, and we are starting to do the paleomag in those rocks. Then something else that's interesting and we are trying to do is to understand better how those speleothems acquire magnetization. And this is the project by PhD project of Janine Carmo. And then going further in more detail in the stalagmites, we are going to use magnetic microscopy to get much higher resolution in terms of the variation of the field. So instead of having 30 years or 100 years, we are trying to reach the year level record. And of course, it's going to depend on how many magnetic materials are going to be in each layer. But the idea is to go as far as we can in terms of resolution to get a better understanding of the variations of the magnetic field. So this is just to give you an idea of how we can do what we can do with that. Here's the tip of a stalagmite, of the Alio stalagmite, that responded to this variation in density. We are going to talk, this corresponds to the last 200 years. And this is the map of magnetization that can be obtained for this tip of the stalagmite, showing that very nicely that the layers that are well mapped, this kind of let's say a magnetic map of aeromagnetic map, but at the micro scale. So I'd like to thank everybody. Here we have our sponsors, people that the FAPESP, CNPq, CAPES, and all institutions that helped us with those works. And here's the team that you already know from the talk. Thank you very much. And I'm here to answer any questions that you have.
Yep. Bueno, muchas gracias, Ricardo, por la charla. Así que bueno, vamos, si alguien quiere hacer preguntas, puede levantar la mano o hacerlas por el chat y las leemos en voz alta. No sé si alguien...
Fernando, ¿pueden hacer preguntas en portugués, español o inglés?
Yo creo que en todos los idiomas mejor, porque en inglés yo por lo menos no... Augusto.
Yeah. Ricardo,
Sí.
congratulations, very nice talk. I learned a lot of what you're doing there. I have just a question about what you think about these results in St. Helens, because it is, for me, I read the paper, it looks very interesting, but it seems to be a very speculative jump, yeah? To go from this high high dispersion to high secular variation, and then from there to the South Atlantic Anomaly. What do you think about?
Yeah, it's a big shot. I fully agree. In fact, it's my impression is that she was expecting for that. Like she was trying to test if there was something anomalous about the record, and the record is anomalous in terms of dispersion, isn't it? But there's if you go through the paper, you're going to see that she tested also the consistent within the sites. And also she tested if those more dispersed directions were or were not transient field. And I think she has a good point that those are not transient fields, the ones that she considered in calculating this dispersion. So I think that, of course, it's a big shot. Of course, it's very hard to tell from that if this is really something close to the geomagnetic anomaly of the South Atlantic or a South Atlantic-like geomagnetic anomaly. But that's why I think. But I think we need to test with other records in the region. If it comes to the, if it, in the end, we come up with the fact that all the islands in there and some sedimentary results from those islands, because there are lakes in some of those islands, they all show anomalous dispersion, then I think we have a point. We have something that stands out from the gem model, and then may really indicate that there's something happening in this region.
Do you know if they are getting some paleointensity results from St. Helens?
I hope they are, because the other paper in Tristan da Cunha, they got some paleointensity, very few.
But there is just a few tens of thousands of years, yeah? And then you jump to 10 million years.
Yeah.
It's a big jump. But it's really interesting.
Yeah, but you know, if that's true, if the anomaly is recurrent and it's related to the velocity anomaly, you know, to the heat flux anomaly at the core-mantle boundary, there's no reason that this anomaly is not there for tens of millions of years or even more. Because the anomaly is sitting there for hundreds of millions of years.
Yeah, interesting. Thank you, Ricardo. Muito obrigado. Muito obrigado.
Thank you very much.
¿Más preguntas? Yo tenía una pregunta también. Al final, ¿qué es lo, porque estoy muteado o no? ¿Qué es lo que hace que la anomalía se vaya moviendo tan rápido al final? Con respecto a los movimientos del manto, que son mucho más lentos, o del núcleo, del límite manto-núcleo. Al final la anomalía se mueve muy rápido con respecto a las velocidades que actúan en el interior de la Tierra. Entonces, ¿por qué esa diferencia? Esa es un poco la pregunta.
I was saying in English, okay? The last paper by Felipe Terranova, he explores that. In fact, the 200 years that take for the anomaly to go to Namibia, from Namibia to Paraguay, is really very fast. And the explanation he gives is that the anomaly moves because there is a kind of balance between two flux patches. There's a big flux patch at the continental boundary that is close to the South Africa. There's another flux patch that is in South America. And there's a normal flux patch very high in the south to the South America. So those three flux patches, they change in intensity. If the flux patch in Africa is very high, the anomaly goes there. Then if it decreases in intensity and the flux patch in South America goes up, then the anomaly crosses the Atlantic and then goes to South America. So it's related to the relative intensity of those two flux patches that the anomaly moves from one place to the other. So that's the explanation we are providing now. That's why we think it's very fast. It's not the anomaly that's moving, but it's the change in intensity between those three anomalies.
Gracias, Ricardo.
Yeah. De nada.
Hay una pregunta ahí de Sanja Panowska. Great presentation, many thanks. Short question, are there new paleothemes that cover periods of excursion, low jump, monolake, Blake, or others? By the way, I followed recently a Zoom talk by the author of the study of St. Helens, and they are measuring intensities.
Oh, she's measuring intensities. Okay, good. Hi, Sanja. Very nice that you saw the talk. There are some works that have been done in the Blake, and there's this work of Lascaux and Lacham. We are trying to get some results from also from a Lacham period of time. So there are some published results from some excursions, and we are trying to get some other results from excursions, but there are not that many. But there is a paper that was published in 2018 by a Chinese group, and Andrew Roberts is one of the co-authors. There's a paper published by Maria Osetti from Madrid. So those are the papers that I know that that show records of excursions using speleothems. I would like to draw the attention of Sanja also to this result that I think is interesting, is that we have those very high intensity results from they were first observed in Israel, and then they were observed in Spain, in other different places in Europe, and they are also correlated with very fast changes in orientation, and we seem to observe the same thing in Morocco as well. So it means that the speleothems, they can record on not only the excursions but also those very fast variations of the geomagnetic field at the scale of hundreds to thousands of years.
¿Más preguntas para Ricardo? ¿Alguien más?
¿Puedo hacer otra?
Sí, dale nomás.
Ricardo, you show the present day extension of the anomaly, which covers all South America and goes into the Pacific Ocean. So Chile is well inside the anomaly, at least yes. Central and Northern Chile.
Yes.
If we assume that we are not shut, if we assume that this is a regular feature of the Earth's magnetic field for hundreds of thousands of years or millions of years, we should assume that this is typical. Yeah, this is a typical South Atlantic anomaly. And so, well, Fernando has thousands of lava flows of the last 2 million years in Chile. there should be some kind of results similar to those of St. Helens in Chile, unless we are just in some very exceptional South Atlantic anomaly that and in the past never reached Chile.
Yes.
Well, I think that's a very interesting thing for Fernando and you to go there to Chile and try to do very detailed studies on the volcanics there, because there have been a lot of studies in recent lavas, but mainly in Patagonia, I guess, if I am not wrong. So
exactly.
Maybe Patagonia, you may say, well, look, it's not so much inside the anomaly, but perhaps also there are some volcanics in Argentina too, of 1 million, 2 million years, which may be also interesting to see what happens.
Yeah, I fully agree. I think that that's a very interesting subject to go forward, because there is a model by Aubert in 2016 that he suggested the anomaly crosses South America and goes to the Pacific. He was trying to do a forecast how the anomaly is going to evolve through time. So yes, that's going to pass through northern Chile and goes even to close to Bolivia and Peru. So having lava flows from those regions would be very nice to test if the anomaly is going to pass throughout those regions, and also do the same thing that we have seen that people have done in St. Helens, calculate the dispersion, and see if the dispersion is really anomalous as well. There is something very strange about the dispersion. If you look at the Cromwell paper in 2018, is that we have much larger dispersions in the southern hemisphere than in the northern hemisphere. And lots of the results in the southern hemisphere are in South America. So I don't know if this is somehow related, but that's something that we could do.
Okay.
It's a Latin Mag project.
Thank you, Ricardo. Great talk.
Thank you.
¿Más preguntas para Ricardo? Bueno, si no hay más preguntas, Ricardo, te damos las gracias por la presentación.
Ricardo, posso fazer só uma pergunta em português?
Sim, por favor.
Apresentando o Brasil aqui um pouco. Não, então, a minha pergunta é, na verdade, para saber se nesses cálculos de variação rápida já foi levado em consideração um trabalho de 2013 da Agat, que a Cláudia também faz parte lá da Patagônia, né? E daí lá eles pegam, eu não sei, o final do Pleistoceno tardio até aqui, né? É um testemunho enorme e que, de repente, daria para fazer algumas tentativas de achar, sei lá, se teve recorrência mais para trás no tempo, pelo menos em termos direcionais, que, né? De repente poderia ser feito isso também no trabalho dela, que eu acho que é bem interessante. Tem né, bastante dado e qualidade também. Não sei, só um comentário, na verdade. Não sei se você tem interesse, mas eu acho que valeria a pena pensar nisso.
Legal, Wilbur. Vou continuar respondendo o meu inglês quebrado, tá bom? So it's a very nice idea. The question is that the Potroc Ike Lake is very south in Patagonia. So I think it's out of the South Atlantic Anomaly region of effect. You know, maybe it's I don't know if it's going to show the signal that people see in St. Helens, because St. Helens is exactly on the track of the anomaly. But notwithstanding that, it would be nice to see how the variation, how the dispersion behaves in that lake, because then you can compare that with some other places that are exactly on the track of the anomaly. And I agree with you, the result is very nice. The result that Claudia Gogorza and Agat these pronovos they obtain is remarkable, very, very nice. I think it's the best record for the sediments, young sediments in South America. Obrigado, Will, pela pergunta.
Bueno, ahora sí, si nadie más tiene preguntas, ¿alguien más? ¿Augusto? ¿No? Le damos nuevamente las gracias a Ricardo por la interesante charla que nos dio. Y nos vemos entonces en 2 semanas más. A esta misma hora más o menos, ahí vamos a avisar la hora por mail nuevamente. Así que muchas gracias. Chao, Ricardo. Chao a todos, que estén muy bien.
Obrigado a todos.
Buenas noches.
Thank you so much.
Chao, chao.
Thank you, Ricardo. Thank you.
Oh, thank you, Chichi, for being there.
Thank you. Good to see you. Take care.
Good to see you. You too.
Ricardo, manda-me tua palestra, teu PowerPoint depois, se puder.
Claro, Eric. Bom te ver, cara.
Bom também. Olha, temos uns resultados muito interessantes aqui também, nos modelos de uma estalagmita aqui em Portugal. Depois a gente conversa.
Oh, perfeito. Manda um e-mail, a gente conversa.
Tá bem. Vá. Fica bem.
Um abraço para todo mundo.
Outra.